Good afternoon, PyCon. Just a couple of announcements before we get started here. Just like to remind auction winners to pick up their winnings. Go right down to the registration desk now if you won an auction last night. And I would just like to mention the sprints. We'll be holding the development sprints from tomorrow onwards. Anybody who wants to contribute to the library, meet authors, etc., please stick around for messages after the lightning talks for an introduction to the sprints. And if you'd like to lead a sprint, please prepare a short 20 seconds only description of your sprint and be prepared to give that after the lightning talks. Okay, I would like to present Hannu Krosing, and he's going to tell us the PostgresSQL, it really is web scale, smiley face.
So, hello. Nice to be here, one of the last talks, I think, in this conference. And I'm going to talk about scaling Postgres, first what it is, how we scaled it at Skype, what new ways to scale it have appeared since, and also I have tried to push in some more stuff about using it from Python, so I need to go really fast in some places. Fortunately, Craig already spoke about some things I had put here, so I can skip over these really fast. And so let's get started. So, I am Hannu Krosing. I currently work at I'm a Python user since about version 1, maybe a little before. Postgres user since because before it was even SQL. I did some tests with a very old version of Postgres, which used a language called PostgresQL, so it was essentially a NoSQL database, even though it was already then a real relational database. I'm a small-time hacker and contributor to both Python and Postgres. Both have small amounts of my code in. I was first DBA and database architect at Skype. Since leaving Skype, I have been full-time PostgreSQL consultant at Second Quadrant. Second Quadrant is, I would say, the company that employs largest number of top PostgreSQL developers. We also do support and so on, so if you need some high-level help, then come to us. And I also am a technical advisor to the investment company of the Estonian founding engineers of Skype, so if they have some interesting stuff, then I help them to evaluate it. I have also written 2 books on PostgreSQL. Is it? Ooh. Okay, I see that it kind of echoes. Not sure what to do about it. One of them is about PostgreSQL administration. I wrote together with Simon Rakes, who is the head guy of Second Quadrant. Also, I wrote a PostgreSQL server programming book, which basically tells you how to write stuff inside PostgreSQL server that runs using Pl PGSQL, Pl Python, C, Pl Proxy for scaling, and so on. So, what is Python? Okay, actually you know what Python is, so I won't go into that. But it's a really nice and universal language for almost everything. What is NoSQL? NoSQL is usually mostly it's a storage. Sometimes it has some language in it. It can be a simple key value storage, key structured values, graph databases, distributed caches, some that do use SQL, so probably some would call what I am describing later as scaling here also, that it's NoSQL in sense of not only SQL. So why people use NoSQL? First, it's simple to implement. It's quite often the reiteration of the old team that let's use files for speed, which works at small scale and doesn't work very well at large scale. Nowadays, some NoSQLs have matured to quite large usages. It's also simple to get started, simple to do initial development, and it is a scalable storage layer. What are the things that NoSQL usually sacrifices compared to using a real database? First, the 4 big things that databases offer, relational databases, are atomicity, consistency, isolation, and durability. Atomicity means that everything either happens at once or doesn't happen at all. Most of NoSQL databases have some form of it. Quite often, or most often, it's done just by locking everything in the collection, then so that you can have it all to yourself, and then usually at least have a single statement rollback. Some have also transactions, so that you can have multiple commands, multiple updates rolled back together if you didn't like them. Consistency is something that most NoSQL databases by definition don't have. They are schema-free, so there is nothing to be consistent with. Isolation, again, which means that others either see everything you did in transaction or see nothing. This is, again, quite closely tied to atomicity, and meaning that because you do it using locking, then you usually have it by excluding everybody else from the database for the duration of time. And the durability in many NoSQL databases is actually replaced by replication. They tend to have some kind of local durability, but usually it is implemented in quite slow fashion. It's either a sweep or in-memory data every few seconds, or is it some type of write-ahead log, usually, again, not really fast. So what is PostgreSQL? This is the database I mostly work with and have learned to love. PostgreSQL is a mature relational database management system, database engine. It has been in development almost 30 years. Last 20 years as an open source project with a very active community. It's from the very beginning, it has had a highly concurrent design, and it has full ACID guarantees. And it has also an ANSI standard SQL language implementation, but it's not everything it has. So, and if we want to get already to do some sacrifices of PostgreSQL, then there are things that we can switch off or do without. Atomicity is always on. You can't commit half of the work, or it never happens that, for example, after a crash, some of your work is visible, some is not. You can do without consistency. You can leave out foreign keys, unique, exclude, not null, and other checks. If you don't want any data checks on your models, then you can use JSON, XML, or HStore. So you have full freedom to store whatever you like in your databases. Isolation is always on. Again, other parallel users can't see your half-done work. They either see all or nothing. But you can switch off durability in many levels. You can use asynchronous commit, which means that you have a few milliseconds of failure window. If crash happens right after you did commit, you may lose some data. Or for much more speed, and but with the caveat that you can lose all the data, you can use unlocked tables, which means that the tables are written only once. There are no guarantees that they will be there after crash. But under normal operations, they are there just fine and also follow all normal rules. So Postgres is much more than a storage layer, but it has a very good storage layer built in, and you can use it as a simple storage if you so wish, if you want to write your applications in the typical NoSQL style. And which usually means that you have to create the complex parts like locking and concurrency control and joins and more, lots of complex stuff in your application. It will be a bit hard, but sometimes it's good for scalability. For example, if you're moving from an existing NoSQL database to Postgres, then you can start exactly as you were and move to more performant, more consistent ways later. I did some tests comparing Memcache, Readies, PostgreSQL, and MongoDB. The top lines here are Memcache and Readies. They are basically, Memcache is non-consistent. Readies is non-durable. Readies is kind of durable. It runs, it stores its data every few seconds, every few tens of seconds. And it gets performance like this. This is PostgreSQL's read performance. This is PostgreSQL's quite stable write performance. Not stable, durable. It's done with async on, which means that you may lose a few milliseconds. If I would have used non-log tables, I guess the performance would be around here. And these top lines are MongoDB. Again, this may be a very good representation of MongoDB because it's a single database, MongoDB. What is representative is the lowest line, which is the durable storage MongoDB, which is somewhere around here. Even at 64 parallel clients, it's still only a few thousands, whereas Postgres is 40,000. Inserts or sets and gets per second. This is primary key with one index and JSON data. So, well, Craig already went over these, all kinds of good and hackable features that Postgres has. It is really built as a platform, not so much as just a database. You can redefine everything. You can influence how it works really well. And when using PL Python, you can also do quite easily ORM-like things. For example, it's not very hard to write a small thing that lets you replace your selects with some metaprogramming, and then you can make your tables look like they were arrays of, or collections of classes, collections of rows. Okay, there is more, but now let's get to scaling, which we won't have time to talk about anyway at all. So when Skype started to grow, then it happened about the same time as Amazon and Google developed their large database solutions, except that we did it based on Postgres. First to do some vertical scaling split by functionality. At some point, this doesn't work anymore. Then you start sharding tables, especially if you have write mostly loads like we had. Skype buddy lists were things that were more than 90% writes because they are seldom read, only when you go to a new computer. Otherwise, all the other time they are just written to. And once you have gone to sharding, you can undo lots of your original changes and you move all user-related data to the same shard, so you still have consistency inside the shard. You can write simple SQL, simple programs in other languages to work close to the data. And we were able to basically maintain from the client's side view as if we had a single big database. And we had one of the ways we did was that we did all access to the tables, or to the databases as functions, which means that the clients never saw any tables. If you connect as a client user, you don't even know that tables exist. All you see are functions, which and we basically just, if we needed to call another database, then we used Python for that. We used PsychoPG, connected to another database, queried there. It ran in really 2-3 milliseconds, so it wasn't a performance problem. And and then the first one was for vertical scaling, when we, for example, just needed to look at somebody's account from another database. At the horizontal scaling stage, when we couldn't fit a table in a single database anymore, then we started selecting the actual database connection inside the function and querying there. And if we, after we had done that often enough, we invented a special language for it, which basically the source code is about where to run the function. And we had 2 iterations of it. First was kind of one big blob of code. Then Marco Crane rewrote it and split out the Pl Proxy connection pooler and then the Pl Proxy language proper. And after that, almost everything at Skype was written in a sharded manner. You have the exact same function written in either Pl PGSQL, PySQL, or sometimes Pl Python on the shards, and then you have the proxy functions on many proxy machines, which can be the same machines as servers, or as the databases, or can be separate machines. And then you connect to any point, and you get the data from where it's actually stored. So, okay, quick. Basically, why is poor functional interface good? First, it's good for security. It's also good for maintenance. You get really clean separation of interfaces. If you need to fix something, you don't need to shut down clients. You just redefine the function, and clients can continue as before. So you don't need to schedule downtime for upgrades on the database side. Of course, you need to test before. And also, if you need to some kind of instrumentation added to database, then it's easy to add to functions. And as we found out in the end, it was also easy to scale, because you could do it easily by developing a language, Pl Proxy, and then starting using it for everything. So. And we solved the problem with functions being too limited, that we initially let our web developers and all developers write their own functions, and only when the product was deployed, then it went to DBA staff, who then could fix stuff and make it more performant if needed. And the good thing part of Pl Proxy style sharding is that in the end we still can write code that only runs in one access in the database. It can do stuff to many related tables. It's all consistent, it's transaction controlled, it has full ACID guarantees there. And if you running from Python, then you can write easily decorators, so that you basically, in your code, can just call the database functions as if they were your local functions. This is also I have done it a few times. It's not hard. It's just look up how decorators work, and it's done. Okay, here is a sample how Pl Proxy works. It can just proxy calls, then you give full connect string to another database, but it also can select a database based on sharding, say hash text of username, or select geographically closest database, or basically it can be anything. You can also have a function that returns a connection string based on the day of time. And for example, if you want to take some master database down for a night, then you can do it and only allow access to read-only databases at some times. It's easy to set up. You have 3 functions: partitioning function, which basically returns a power of 2 connect strings, cluster version functions, which is the one that's always consulted, and if it changes, then the partitioning function is called again and cached. And there is also a possibility to have a cluster config read from function. First, there is partition function for 2 partitions. It can be, and usually is more than 2. There is cluster version function. Basically, after you have changed the partitioning, you just redefine this function to return another number. It must be bigger than the last one, so the configuration will be reloaded. And if you want to set some options, then you set the options. And now, because these functions know the cluster name users, then you can easily just say that use cluster users, run on hash text username, and when you run it, then the function gets called in the right shard, does whatever it is defined to do, and then comes back. And with modern fast networks, this extra hop adds usually less than a millisecond to the whole round trip of the query. So this was how you already have a scaled database. How we deal with scaling is that you define more shards in the beginning than you have actually physical machines or physical databases. First you allocate a larger number on each. Then when you need to move, you move only a few shards, and then, for example, from 2 to 4 partitions in a few steps. This is how you end up. And basically, the actual moving is done with logical replication. The tool we developed is in the package Sky tools. It's called Londist, which is a name of a toy elephant from an Estonian children's book, because everything Postgres has is somehow related to elephants. And basically you set up replication and then wait however it takes, how long it takes, and then you have something. So, but if you don't have functional interface, then there is a nice thing in Postgres called foreign data wrappers. Basically you can write a function originally in C which presents a table interface to Postgres. And some nice people have written a tool called Multicorn, which lets you do this in Python. So you write the Python class and then expose it as a table to Postgres. It comes built in with SQL Alchemy, CSV and file system, foreign data wrappers, access to IMAP, RSS, LDAP. There are samples that expose your Google mailbox as a table, so you can query them from database. For sharding, for anything, you basically need to write a class in Python and then expose it like this to the database, the Postgres. First you create the extension Multicorn. Okay, you don't need to drop it because it didn't exist, it's from my code. And then you create the foreign data wrapper, and then you create the foreign table using this wrapper. And then you can just query from it as much as you like. This class has a few functions. If it's read-only, then you need only execute method, which has quals and columns. Columns are column names. Quals are actually triplets of column name, operator, and value. You can use these to limit how much data you return, how much data you get from external stuff. External database, in this case, I am doing, again, a thing very similar to Pl Proxy. Basically, I select based on the value of a column, and then return only rows that, and then from this partition, I return the rows that are needed there. Same for insert, update, delete. You have also transaction control. At the end of transaction, you can do commit, rollback, pre-commit if you want to do two-phase commit. So the basic blocks are there. And the nice thing with this is that you can, different from PL Python, this actually can do streaming, so you can define an infinite table and then select only first 10 rows from it, and it doesn't blow up your database as does PL Python set returning function. Okay, almost in time.
Okay, we do have 3 or 4 minutes for questions. No takers? Okay, thank you very much, Hannu.
Thank you.